Here are two lists that look identical. Change one element in one of them and the other one changes too, even though you made a copy, not an alias, an actual copy made with Python's copy library. Today we find out why copying a list of lists only copies half of it, and what to do when you need the whole thing. Every list so far has held strings, integers, other immutable things. Now let the elements themselves be mutable. Take old list, 3 elements, and each element is another list. What those inner lists hold does not matter yet. What matters is that the top level holds exactly 3 things. Here is the detail that changes everything. A list slot never holds the object itself, it holds a reference to it, and once that object is mutable, that reference is the thing you have to think about. So old list is one object holding 3 arrows, each aimed at a separate list, living somewhere else in memory. 3 operations act on this structure: aliasing it, shallow copying it, and deep copying it. Case 1, a plain assignment. New list is set to old list. No copy function, no slice, just the equal sign. Python builds nothing new. It writes a second name onto the same object, so both names point at that same list of 3 arrows. Now run the line that indexes new list at position 2, counting 0, 1, 2. Then goes into that sublist at position 1 and sets it to the number 6. That slot held the string foo. Follow the arrows. New list reaches the shared top-level object. Position 2 reaches the third sublist, and the position 1 inside it becomes 6. Print old list, and the 6 is there as well. One object was mutated, and both names see the mutation. Aliasing is not the only option. You can copy a mutable object, and there are 2 kinds of copy: shallow and deep. Take the shallow one first, import the copy library, then call copy.copy on old list. Writing old list followed by square bracket colon does exactly the same job. For the flat list of the earlier videos, the slice really was a complete clone because every element in them was immutable. Now the elements are lists themselves and the picture changes. For this example, old list holds the sublist 1, 2, then the sublist 3, 4, then the sublist 5, 6. Python duplicates the top level only. New list gets its very own list object with 3 slots, and that part is genuinely new. But the 3 arrows inside it are copied as arrows. They still aim at the same 3 sublists. Nothing below the top level was duplicated at all. Test the top level first. Append the sublist 7, 8 to old list. Python follows the name old list to its own top level object and adds a 4th slot on the end. New list has a different top level object, so nothing about it changes. It still holds 3 sublists. Print them side by side. Old list now shows 4 sublists, new list still shows 3. That is the half of the copy that genuinely worked. 2 independent top-level lists, appending to one, deleting from one, reordering one. None of it reaches the other. Now reach one level deeper. Go into old list at position 1, the middle sublist, and inside that sublist, at position 1, change the 4 into the number 9. Print new list. It shows 3 sublists, 1, 2, then 3, 9, then 5, 6. The 9 is sitting there, inside a list you never named. Print old list and you see the same 9, plus the extra sublist 7, 8 that you appended earlier. So one statement was invisible across the copy and the other was not. And the difference is the level each one acted on. The append changed the top level object, which belongs to old list alone. The 9 changed a sublist object, and that object is shared. Both names hold an arrow pointing straight at it. Here is the rule in one sentence. A shallow copy duplicates the top structure and nothing underneath it. Any element that is itself mutable is not recreated. The new slot simply receives an arrow to the same object. That design is deliberate. If Python rebuilt every level, copying a deeply nested structure would mean duplicating an enormous amount of data for a single assignment. The sharing also runs both ways. Edit one of those sublists through new list and old list sees the edit because both names reach the same object. Only the sublist 7, 8 appended to old list alone stays invisible from the other side. Now change exactly one thing. Call copy.deepcopy instead of copy.copy. Everything else in the example is untouched. Deep copy walks the whole structure and rebuilds every mutable object it finds at every level. New list gets its own top-level list and its own 3 sublists. Not one arrow is shared. Run the same 2 statements again. Append the sublist 7, 8 to old list, and only old list grows. Go into old list at position 1, then position 1 again and change the 4 into 9 and only old list changes. Print both. Old list shows 1, 2, then 3, 9, then 5, 6, then 7, 8. New list still shows 1, 2, then 3, 4, then 5, 6, exactly what it started with. You can check every claim instead of trusting the diagram. Python's built-in ID function reports the identity of an object, and the 2 names produce the same identity only when they point at the very same object. After shallow copy, compare old list and the new list themselves. Different identities, 2 real objects. Then compare each sublist through both names. Identical, all 3. Repeat the experiment after a deep copy and all 3 sublist identities differ. The actual numbers change on every run and on every machine, so never read anything into their values. Same versus different is the entire message. 3 things to carry away. First, the mechanics. Copy.copy does what the square bracket colon slice does, which is 1 level, and the deep copy goes all the way down. Second, and the bigger, there are objects sitting in memory, and there are names pointing at those objects. Hold those apart, and aliasing, cloning, and iterating all stop being mysterious. Step these examples through Python Tutor, and you can watch the arrows move for yourself. Third, side effects. Every operation here has one, and the job is making sure you never change something you did not mean to change. That is also how to choose between a list and a tuple. Reach for a tuple when the data must not change. If it could be modified by accident, do not store it in a list. Reach for a list when copying is the expensive part. With a large database, mutating one field in place beats duplicating the entire structure for every small edit. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.